We are very
Hello,
happy to get
hello,
this
Ratan.
meeting going with quite a large number of attendees, I'd say, for the start. This is something which I thought I will organize, getting people over the world, and but mainly from Indian Railways because I belong to the Indian Railways originally, and we have got friends working in this field of CBTC, which has become very important. So the pattern of the meeting is what I show in the agenda. I believe it can be seen. The At this meeting, this is not going to be one meeting basically, but we shall start with this today. We are going to first get Arun Saxena, or who. See, I'll just give a quick introduction to our participants. So, participant mean the panelists. Arun is the or has been a very experienced and a key decision maker. He is a railway engineering professional with 40 years of experience in the development and approval of design, installation, testing and commissioning, maintenance and operation of signaling and train control telecom systems. He also obviously has a great insight into the system architecture of things which make the signaling systems like a software embedded systems, then the signaling schematic plans and systems which can provide which can work in a safety critical and secure manner. He has held many important positions in his career. Before he retired from the active service, I'd say rather from the railway service, he was the general manager of the North Central Railway. He had worked as advisor and the executive director Signals and Railway Board on the Indian Railways. He had been working as he has worked as a divisional railway manager. He has been working as head of a new unit of modern signaling systems in Reltel just after he retired from general manager. So he has in this roles obviously a very good exposure to things which make a railway system, how the decision makers work is exemplified by him. So he will give some insight into how the CBTC systems are decided. And then we move on to Mr. Ratan Mukhopadhyay, who has been who had worked before in almost 20 years, I believe, before today, as a chief signal engineer on the Eastern Railway, from where he retired and went to Malaysia to work as a project manager there on an onshore project of Siemens. I think what they pronounce as Siemens, is it, Ratan? So anyway,
What?
Siemens, he then moved to Siemens, Switzerland, and
Yeah.
had been there for a long time before he came back for his personal convenience to Malaysia, and he remains a member of the Circle of Expertise in Siemens, Switzerland. He's also a chief technical officer of ASAP Mobility Malaysia, which is a great position to be in there as a man. He's a very recognized person, having he is actually a he is a system specialist in electronic interlocking, which is for
Okay.
modern signaling systems. So uh,
Actually, mine is
just one.
first. Anyway, let me
Uh,
see.
yeah, sorry. So he is uh, 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 sorry. Some did Arun or some? Yeah. So we also have, or we will see some insights into how these modern signaling systems are delivered. We have got Akshay Malviya, who was originally from the railways, Indian Railways, and he moved over to Australia. I think he must have come almost some 15 years back or so, and he has been working here, and he has been working in various Australian organizations and has a very wide exposure in the industry in Australia. He has managed large multidisciplinary projects in Australia and in India, So he is working in as a senior management. He's in senior management roles in Australian Rail Track Corporation, as well as he has worked on the Queensland Rail and in the Metro Trains Melbourne. So Akshay is a engineering manager with a Tier 1 Australian consultancy and construction company known as the United Group Limited. And we also have our fourth panelist, Mr. Pinak Das, who is a subject matter expert on CBTC. He had joined the Indian Railways as well, like many of us here today. He moved over to the UK. He worked on network rail projects with Atkins, and he worked for various clients in Australia. He has been a very keen design engineer. He has, while he was in Australia, I was very close to him, and he then relocated to UK in 2014. He has been working on various projects of the Network Railway during 2014 to 17. At the moment, he is working for the LM project of the London Underground. He is a CBTC expert, I would say, and he became the contractor's responsible engineer for a network railway. He is also the competency, he is a CMS, competency management system of Thales Canada license for application data for Thales CBTC systems known as CellTrack. So we do have a large number of highly experienced persons on the panel as well as in the ghost, but we will first get a quick glimpse of what CBTC, how it gets done, and then move over to have some technical insights as well. So it will be a kind of about 30 to 40 minutes for the panelists, and then the floor should be kept open for the guests to have their questions to the panelists, and that is how we intend to progress in this meeting. So can I ask Arun to start off this meeting today? Arun, over to you.
Yeah, thank you. Thank you, Somnath, and thank you for the entire group of experts who are on the panel, and a list of I think a very elaborate list of attendees. Many of them are real experts in the area. I would, I think, like to mention from the angle of how CBTC started in India and what strategies we had adopted at different stages and how it has now become a norm in India. So I would like to mention, I think, how much is the time given, Somnath? How much time I can take?
At least do 10 minutes, definitely.
Okay, thank you so much. So I would just like to mention that if you look at the how it evolved, how the mass transit systems evolved. Initially, we all of us know that we had the traditional system of or the conventional systems of automatic block signaling, and we were able to handle traffic with that kind of a situation, that kind of a system, which we could handle headways up to the order of 3 minutes. In fact, Mumbai suburban section is a very good example of having a headway of 3 minutes, both on central as well as western railways, with only tweaking with the inter-signal distances and the aspect control, making it four aspect. And as the traffic started growing and the demands for more and more trains increased, in fact, in other countries already the systems were there, which were, I think, largely ground-based. And the ground-based system, as you know, there are limitations of, first of all, they require very, very severe maintenance regime. And second one is the headway could be large, I think could be managed to about 120 seconds or so. But when the concept of moving block started becoming a reality, then the system of CBTC also started taking shape. And that is how the CBTC thing started, because the frequency of the trains can be substantially increased, especially during the peak season or peak time, or when on demand. So therefore, the CBTC has gradually entered into the system in the, I think, in the year 2003-4, it all started. And at that stage also, the standard also emerged. That is the 1474 standard for CBTC, which emerged in the 2004. But prior to that, I would like to mention that we had plans to have the first metro in India in Kolkata. And the first metro was planned almost 20 years back, that is 1984. And in the year of 1984, we could start initially with the typical absolute block signaling and later on automatic block signaling. But somehow, for some reason or the other, we were not able to really make the full system operational, which is the continuous automatic train control, which was ground-based system. But 20 years later, when the Delhi Metro emerged, almost in the year 2001-2, at that stage, we gave the first in-principle approval from the Railway Board. And that is what I think from the angle of the management and the administration, what the people want to have. The people want to have a system which is standard, which gives the required parameters of headway, which gives you the required information to the customers and passengers, and which is able to precisely control the train stoppages and starts. And this is apart from the basic requirement of ensuring safety that anyway has to be ingrained and embedded in all our signaling system. The safety is anyway a basic criteria. But apart from that, as I mentioned, headway is a very important criteria, which leads to improved frequency, precision stoppage, which is a very important criteria, and minimizing the maintenance effort, and trying to reduce the hardware, especially on the track side. And that is how CBT is emerged. And as all of us know, I think about it, the CBT is the only three components are there. The first thing is the precision location of the train. Second one is the transmission, two-way high-speed transmission between the train and the ground side, track side. And third one is the processing at the onboard as well as on the base side. These are the three components which are very, very stringent. And as the technology evolved, these systems are now feasible and workable. So what ultimately matters today is that how fast we can do it. And today, if you look at the scenario in India, I think metro works are in progress in almost more than 22 cities in the country. And initially, they were going in for the ground-based system, which was distance to go. But now I think after the Kochi Metro and the Lucknow Metro have shown the way, now CBTC and Hyderabad Metro, CBTC has become a norm in India, and accordingly, as we gained experience, the biggest thing which has happened in India is the issue of a document, which is basically a document which was prepared in the year 2013 by the Ministry of Housing and Urban Development and the Ministry of Railways for standardization of signaling and train control systems for metro railway. This document became the base for everything. And based on this very document, RDSO issued a process for certifying safety for running of this train, because on the Indian Railways, initially, all train movements were supposed to be controlled by the Indian Railways Act. Later on, the other acts have come, but the Indian Railways Act was the starting point. And therefore, even today, the technical clearance has to be given by the Railway Board, which ultimately is basically channelized by the metro authorities through RDSO when it comes to the board, which gives you the in-principle approval. And what in-principle approval is, it is basically pinpointing the type of signaling to be used, whether it is CATC or CBTC, and the kind of backup signaling you want. That is also very important today, because that has to be specified at the initial stage itself. And the kind of interlocking you are going to be using. The train control mechanism, as I mentioned, it has to be continuous automatic train control using CBTC. Then whether you need to have a coded AF track cycle, which was the previous system, or axle counters, which is the current system nowadays. And what kind of point machines do you want, whether trailable or non-trailable, whether on the main line or in the depots. And thereafter, what kind of redundancy you expect on the cab. That means on the cab, what kind of availability you want, so that the operations don't get disturbed. Apart from that, there are a large number of telecom systems which have to be stipulated. And with these details by the Metro Authority from the OEM, they are passed on to RDSO. RDSO scrutinizes these documents and recommends to the board the kind of approval which is required to be given. After that, when this has been given in principle, then the detailed system design and activities are done, and there comes the role of the independent safety assessor, where the independent safety assessor gives their report, and on the lines of the Commissioner of Railway Safety, we have got the Commissioner of Metro Railway Safety, and then these documents are given to the Commissioner of Metro Railway Safety, and he then comes and inspects all that. In fact, this is a very complex process. In fact, you have to look at the structures, you have to look at the tunnels, you have to look at the rolling stock, you have to look at the track structure, you have to look at the signaling and train control system, you have to look at the telecom. All the systems have got different procedures and different definitions. And based on those defined procedures, in fact, this document has been now made ready by the RDSO. In the year 2015, they have issued a document which is totally explaining each and every aspect of standardization of signaling systems on metro. And it not only gives for signaling, it also gives for rolling stock, for track, and other systems. So that is how the systems have been evolved. And I believe that India has doing very well in the field of metro system because of this standardization. This standardization has at least given a clear understanding to all the stakeholders, including all authorities and all the OEMs, that what has to be done and how it has to be done and what are the procedures. This was missing in the year 1984. And this actually started after 2002 when the first metro was commissioned. And first metro commissioning process was defined by the railway board at that stage, and for which approval was given by the. I think with these opening remarks, I think I can hand over back to Somnath. We can discuss about other things like how the bidders are selected and how the returns are maximized. But definitely the standards, the process of approval, and the process of allowing trains to run, that is very important for any system to come into Indian Railways, in Indian context for that matter. Thank you so much, Somnath.
Thank you, Arun. Hand it over to Akshay.
It was obviously
because he had
knowing
been,
about how the thing all starts
his
off.
thought is delivered by him. So he would know how the thought and the delivery conflicts are to be resolved and how much of it actually remains unresolved. Akshay, over to you.
Sir, I will be presenting something. Actually, I've got a few slides actually that will be the basis of my presentation, if that is okay with you. Can everyone see this? Sir, can you see this?
Yes, we can see it.
Yes,
Can you
yes.
go to the presentation mode?
Presentation notes. There are no notes actually. So can you see the presentation?
Mode. Presentation mode, so that you can see the full screen.
Presentation mode.
Okay. Slideshow. Okay.
Right, so yeah.
Right.
Is that okay now?
It's better.
Okay. Okay. So, thank you, sir. And my presentation here will be basically Australian focused, and I will be talking about how the CBTC projects are being delivered in Australia and how we should how we are able to deliver a project like that in greenfield areas and in brownfield areas. So that's the focus, and in how things are done in Australia. Actually, I'm driven by that. So just to give you an overview here, the key focus areas for the CBTC project delivery are mentioned here. You can have a look, and I'm going to talk about what we can do in those key focus areas, like what we should be doing, like what needs to be done to make a CBTC project a success. What, in my view, are the prerequisites for making a CBTC project successful. That's what this presentation is going to talk about. The basic areas that are important from that perspective are the specification, the approach to delivery, the competencies of the people involved, and the assurance process. Beg your pardon? Okay. So I will start with systems assurance management and the quality of a project. So in regards to quality, we know that systems assurance management is the key, and we need to deliver a project in such a way that the required reliability, availability, maintainability, and then safety specifications are met, and whatever clients' requirements are, we are able to deliver that. This why we need to meet those things, because the transit agencies' reputations are based on that, and hence the systems assurance is very, very critical for the clients. I'll show you a 40-second video which actually emphasizes the thing that I've just mentioned. Like, we should not be
along the mountain side, and as I go, I like to sing an upside
Hello! Hello! Yes, but
So the message here is clients can't take things for granted. Actually, we need to plan for everything. We need to execute things in such a way that we are not committing any mistakes. So because this is a safety critical system, and then we have to be cognizant of that fact. So what should be the approach to assurance? There is or the area of focus should be structured and systematic. So whatever we are doing, these are the two key words here. Everything should be structured and everything should be systematic, and then only we can make sure that the RAM's targets and RAM specifications will be met. What are the drivers? The drivers are the laws existing in that particular country, particularly the work health and safety, and other safety laws, and then the approach should be risk-based. Until you adopt an approach which is risk-based, there are chances that the project may not be as successful as you would like it to be. And how to assure? There are different tools to assure how a system that is going to be delivered will meet the requirements. We have got standards, we have got requirement specifications, we have got a process that approves equipment to be installed or rolled out on network. We have got procedures and processes, network rules, safety management systems, environment management systems. And then there are some client-side functions as well. Whenever we deliver a product, client's role is very, very important. And then client-side functions, particularly in Australia, relate to design reviews, construction inspections, audits, and independent safety assurance assessment. So that's where the clients contribute to a project delivery. And in Australia, any big project is now being delivered following systems engineering approach. I hope most of the places, like in India, also are now adopting the systems engineering approach. If they haven't done that, then progressively it is going to be done. I'm sure about that. What a system is? The system comprises of people, processes, hardware, software, tools, and then support. So the thing is, when we talk about a systems engineering approach, what it means? Can anyone tell me what it means when we talk about a systems engineering approach? Actually, it means that we should be delivering the whole system, not a part of the system. So all the subsystems of a system need to be interfaced and integrated in such a way that we are able to achieve our objectives. So whole of system approach is something that systems engineering leads us to. And then systems engineering is also known to be a cement between these subsystems, and then that helps us in the delivery of a whole system. How it is done? So there are things like we say in Australia on say I was working on the metro tunnel project, and on the metro tunnel project the systems engineering approach was being adopted following a robust gate review process. And what is that gate review process? It starts from the concept and then goes up to the finish. So from concept through to finish, there are several gate reviews. So it starts with system requirement review, then goes on to system definition, preliminary design, critical design, issued for construction design review, test readiness, integration readiness, and the systems assurance review. So systems assurance is the last activity when something that has been commissioned is handed over to the client. And then all these things actually require some kind of audit, documentation and approvals and then timelines. So the next important thing in the project delivery of a CBTC project is the migration planning. So you start with the migration planning, you devise everything, plan everything, and then deliver it step by step. So the things that are considered here in Australia, actually the most important ones are the staging of a project, and the TNC. TNC is testing and commissioning strategy. And then we also consider what are the greenfield installs and then what are the brownfield installs. And then there is a different methodology to design and install greenfield assets and then also brownfield assets. There is a concept of shadow mode working where we install things in advance in parallel to the existing systems, and then we run these systems in the night actually when there are no trains in the shadow mode, and then we keep testing until we are 100% sure that the system that we are going to deliver is going to work safely. So these are the things we do here. Track occupations is where in India, actually, there is a concept of non-interlocking. In Australia, they call it possessions or track occupations. Then training to maintainers and training to drivers is also a very important area that cannot be ignored. And then asset data update after the system is commissioned, spares, and then as-built documentation. But one thing very important here is the T- process, which is followed everywhere on the bigger projects, and then it starts from T-20 and goes up to T-0. So the actual delivery starts from T-20 is nothing, but the 20 weeks, exactly 20 weeks before the commissioning date. So, and then there are things actually in the operational readiness plan. These things are well defined, and then we follow that process. And in the planning, we also involve the stakeholders. The project delivery phases here in Australia are like this. Several organizations have got several systems, but generally this is what we follow here. Moving on, the concept phase is the first phase where we decide the scope, requirements, and interfaces, functionality, and then risk of a project. So everything is put together. We do a lot of concept designs. Concept phase is very, very big in Australia. So when you do a CBTC project, say for 40 kilometers, the concept phase will normally take about 2 years actually. So once the concept phase is complete, then what you get is this: a structured, apportioned, measurable, and achievable set of requirements. And that's what is the objective of this phase. And it takes a bit of time, but once it is done, actually we know what we are going to deliver. And then preliminary safety and design report is also delivered. We also prepare management plan and then identify hold and witness points, and then also prepare assurance plans. So management plans are several, like configuration management plan, project management plan, comprising of various things in terms of PMBOK, and then design management plan, which is inclusive of competency management plan and then the assurance plan. Systems assurance plans, there are two different areas. One is system assurance and the other thing is safety assurance. So we prepare all those things in advance. Then we move on to the development phase. Development phase actually is basically to do the detailed designs. And once we complete the designs, we prepare requirement traceability report, which or some people prepare a report, some people prepare a matrix, requirement traceability matrix, because we are following the systems engineering approach. Then we identify hazards, and then also we design controls to manage those hazards, and then we develop assured designs, and finally we do a constructability review of those designs. What is the outcome of the development phase? It is a demonstration that if the project built as designed, then RAM's requirements will be met. That's the outcome of the development phase. We complete the final safety and design report, we complete the safety case, and then the TNC, testing and commissioning strategy, is finalized by end of this stage. During this stage, the clients review the designs, and then also the clients engage an independent safety assessor to do the assessment of the designs. Implementation phase is very critical, but it's not as involved as I would say a concept phase or development phase. In the construction companies generally work independently once all the designs are done, and then they are IFC'd. The IFC designs are passed on to those constructors, and then they generally do step by step, and then that's not that much complicated as the concept and then development phases are. So you can see here the construction, assure construction to make sure that as built meets the design intent. And then also in this phase, actually, there is a go, no go determination that is done based on. So that is also done in T minus, following the T minus process. We start at T minus 20, roughly at this stage of T minus 12 or T minus 8. We determine whether we should be going ahead with the commissioning or not. And then that is called go, no go determination. And all the logistics and everything are planned at that time. And the stakeholders and end users are continuously apprised of what is happening, when the changeover is taking place and things like that. What are going to be the impacts, environmental impact and system impacts and everything. So that's how it is done. And then what is the outcome of the implementation phase? Nothing but the final commissioning and on-time handback of the system. So track occupation is the start of delivery, and then handback is the on-time handback is the end. And then there is a requirement of post-commissioning maintenance, which is always there and everywhere. A finalization phase is nothing but handover, as-built documentation, contract finalization, and then project closeout. And then during this process, actually, we identify the gaps in the standards and then update them. And we also create new standards where needed. So when you are delivering CBTC on a network for the first time, the existing standards will not be or cannot be fully used. So there will be several gaps in those standards. We need to identify those gaps and close them. And then also we need to create new standards for CBTC system if it is rolled out on an existing network. System life cycle. This is a summary of what I've said, that starts from concept, goes through the development, implementation, finalization, and then finally the revenue phase, which is nothing but the operation and maintenance phase. That is it from me.
We'll take the questions at the end because the people will have a better understanding of where to direct the questions to. Obviously, from what Arun has started, Akshay has finished, but in between the two important stages are there somebody who has to create the technical architecture and somebody who has to do the detailed designs. So we have Ratan to tell us something about getting the architecture in place so that what you want to implement actually has some physical realities in place before you start really doing the documents and all that, which is obviously needed. But let us go to Ratan to hear about what architecture he would choose to put in a CBTC, rather the consideration, not the architecture in this time. So over to you, Ratan.
Okay, good afternoon to India and good evening to Australia. Now I take over. So I'll go through quickly because time is 10 minutes. One glimpse of CBTC architecture and the functions. Now, we all know that in CBTC, for that matter, in any train control system for metro railway, we have ATP functions. These are the vital functions, and the automatic train operation function. These are non-vital functions generally, and ATS is train supervision in our
Can
system.
you switch over to slideshow mode?
Pardon?
Switch over.
Are you not able to hear?
No. You go to the slideshow mode. You are having the notes in between, right?
Oh, I want to
You
see.
see, you choose the slideshow. You just click the slideshow.
I can go to the slideshow, but I want to flip. I have other things.
Okay.
Okay,
you flip. That's fine.
Are you getting
Is
this?
it right?
Okay,
Yeah.
okay. One moment. Okay. Can you see this?
Yes.
Okay. So ATP functions, these are all vital functions. These are the most vital functions. And if you go to the standards and norms that says that ATP function that must be there always, and ATO and ATS, they are actually optional. We can choose from them. So in ATP functions, the main is that train location determination, safe train separation, route interlocking, traffic direction reversal, your direction in the track section, and of course the train orientation. All these things we have to ensure. And then train speed determination, safe braking model, emergency braking. These are all functions. We can discuss hours and hours on all these things. Then rollback protections, end of track protections, parted consist protection, door opening protection, interlocks. Door opening means it can be the train door, also the platform doors. Then departure interlocks. So there are a lot of interlocking and protection functions are there. For ATO functions is basically what driver does, but not mainline driver. It's in the metro railway there are additional functions. So automatic speed regulation, starting and stopping, platform bathing, accurately stopping to the stopping locations, and all this. And ATS is normally that the user interface and what we have in our OCC, that kind of function like train identification, train tracking, train routing, automatic train regulation, and junction management, energy optimization, and they're all kind of intervention by the operators like stopping trains, skipping, holding. Then TSR, that is the temporary speed restriction setting, or blocking a section, work zones, all this. So all these are the three groups of functions. Of course, the most important is ATP functions, the vital functions. Now, these functions are implemented mostly by various equipments and subsystems. One is that ATS, then wayside, train board, what is in the train, onboard equipment, and data communication. Data communication, it can be, it is also a combination of radio communication and through fiber optic high data communication. So these are the elements. Now, let us see this thing. Now, if you see this, I want to show the specialty of the CBTC system. If you see ETCS system, so this is an example of ETCS system. The ETCS system, because the interoperability requirement is there, that means many, the total system need not come from a single company, single manufacturer. So here, all the elements are very more or less fixed. Like we have a train management system, we have interlocking, we have, for example, GSMR, radio block center. So all these individual elements, and all this network, the radios. So they are all almost fixed. So the architecture, so to say, is almost fixed. Of course, inside interlocking, various companies, they will have different types of interlocking. It can be geographical, it can be based on table, or all sorts of things. But the functions, the interface, those things are all very, very rigidly regulated by norms and standards. But the moment we go to CBTC, the situation changes because CBTC is a proprietary item. It doesn't have to, actually there is no interoperability requirement. And why that is more important for mainline? Because if the mainline, the thing is, if you see the European railway, the train starts from Italy and it goes directly over the Switzerland, then it go to Germany, it go to then, France, it goes all these countries, and every country has different system. So there it's important, but our metro railway is very, very small and very closed. So that's why one advantage of this thing is CBTC can implement a lot of special function like moving block function. We have to go to ETCS level 3. We don't have that. This is ETCS level 2. So because it is proprietary and the system is a little bit closed and no interoperability requirement, here the architecture, it can be different. It is flexible. Even if you see the norms, like 1474123, all this, if you read, there also, it is not clearly defined that this should be the structure and this will do these functions. So that's the background. Now, to general type, you see the architecture with separate interlocking. You can have a separate interlocking, and that interlocking is connected to wayside system, and this is ATS, and this is train-borne, and train-borne equipment, that is a signaling equipment, is connected to the train subsystems, TIS. And here the only difference is no interlocking. Interlocking is integrated in the CBTC wayside, and it is directly operating the points and not only points, all the field elements, I should say. So if you see the choice, if we go here, let us see, so this is the Bombardier. Now in the Bombardier, this is the, if you see, this is the ATS part in the OCC, and here is the so sorry, one moment. So the top part is the ATS part, and here is the wayside equipment. And you see the wayside equipment, this R is regional. This is the ATO. ATO function is there. Then ATP function is there, then interlocking function is there. So this is all combined. And the RAID is vital system. So this is one rough architecture, and these are the field elements. You can see the axle counter and switch and all these things are there. And this is the train. And here you can see the radio communication. This is going to the train. And there also, if you see in the train, if you have the vehicle ATP or ATP function, and then there's the ATO function, and vital function, it is through safety delays going to the train vital interface. It's a braking system and all other systems. So I think these are all well known, this tachometer. I'm only trying to show you the differences. So this is the Bombardier. Now we go to Siemens. You see, in the Siemens, they have used a separate interlocking. You see, this is the interlocking subsystem. So this color you can see. And they have the ATS subsystem and ATC. ATC, of course, is the ATU, everything is inside. And then data communication system. And this part is the onboard. So if you compare with the Bombardier, you see the functionalities that I showed in the beginning, the ATP, ATU, and everything will be implemented by this system. But their architecture is not the same. So again, if you go to this is Thales, they have many versions. So again, I just want to show you. This is also a little bit, they have got interlocking, and there's a remote control, all this thing. And they call it zone controller. So every company also give their special name, like in Bombardier, they have said regional ATU and ATP and ATC. They call it zone controller. So the terminology also will be different. Architecture also will be different. Okay. Now, I want to give you certain examples that certain ATP functions that is allocable to wayside and train board. So like safe train separation, this can be implemented in the wayside equipment or in the train-borne equipment. And what it has is the main sub-function like determination of the location of the CBs. You see, for train separation, every train here, if you see in this subsystem, here the train is communicating with wayside, but this train is not communicating with the next train. So wayside, he is getting all the information from the different trains, and it knows the position. This train-borne equipment train reports the position to the wayside, and in wayside, all the positions are there. Where is the next train? Then it creates, it generates, checks the from the interlocking where the route is set and direction is okay, and there are a lot of checks that I have already listed the functions. And it issues a movement authority to the train. So here there is no train to train. So here we are coming to a situation where like this. So this is the ultimate what we are trying to do. That train-borne, if train-borne and train-borne talks to each other, if they have communication, then this train can itself generate its own MA, the movement authorities or limit of movement authorities. So this type of architecture, I think the work is going on. I have not got any document, with detailed design of this type of system, but this is conceivable, and it has got also certain advantages in terms of optimizations and all that. So here the basic thing is to take away as much as function from wayside to the train. Train will be almost independent. Of course, the ATS is there, for ATS function that is there. So they say one train is coming and it can order the field element. It can set the field element, and so the interlocking function, mostly it will be there, and some of the things will be there, the wayside and all that. So that kind of architecture is also conceivable. Okay. So, and why this is possible? Because now also with this type of architecture, all these functions, if you see, they can be done from. If you go to the norm, then you can see it is also described like that. That it can be done by either by wayside or by train board. Okay. So, so that is I think the ultimate thing. Now there's a futuristic architecture. But here we have to remember the certain wayside elements and functions, minimum functions will be needed. That means when a train is setting a point from the train ordering, then it is not enough to prove that the point is set and locked. You have to hold it other trains also have to, get the information that this point is used by some other train. So one train cannot use a point, should not be able to use. So all those interlocking functions that will be, partially or mostly be done by the train, and some signature or some status will be retained in the point. So if the second train interrogates the point should be able to tell that I am already engaged in certain other movement, that kind of thing. So in this, but everything cannot be concentrated in train. That is because of the wayside equipments. If you see here, like points in any case will be there. If you have track circuits or track vacancy system, which is secondary system, as Arun said, that that's a very important fallback thing, and it's much easier to design system with a secondary track vacancy system. So that kind of system they should be able to communicate. There's a minimum communication. Level crossing, I don't think we have any country has, but this is given in the norm. In exceptional cases, there can be level crossing, but in most of the countries there are flyovers and the guideway. They don't have level crossings. Platform edge door, of course, it has to be in the platform. They have to communicate. And transponders, that the bellies and all other things, they'll be always there in the wayside. They have to communicate. So with this, I finished my presentation, and my idea is to give the background why different architecture. That is because the interoperability requirement is not there. That's the main thing. So that's all. Okay, thank you.
So thank you, Ratan. And I would also, meantime, before we finish the session today with Pinak, we will, after Pinak has finished, we'll go into the questions. But in the meantime, those who have the questions are welcome to put it on the chat window so that the panelists are ready with their answers better when the time comes. Also, before we finish, we would like to have very experienced personnel on this, attending this meeting. We would like to see if we can get some time for them as well. But before that, I'll ask Pinak to take over. Pinak will tell us about what all this high-level architectures finally amounts to, how the train really knows what it has to do. That's where the final thing happens. You have a project, you have a plan, you have a architecture, but Pinak has to ensure the train understands what we all want it to do and don't crash with the one in front. So off you go, Pinak, please.
Yeah, thank you, sir. I will speak without any presentation. So I work for the 4LM project of London Underground, which is probably one of the is a massive CBTC project. I can only give one example. At present, I am working where the target is to have 32 trains in 1 hour in central corridor area of London. 32 trains in 1 hour. So if I do my design, like I work as a principal engineer, mostly I approve the design. Sometimes I check also, but so. Suppose we have done the design 100% based on the requirement. Then also I find when we do the simulation or testing, we find we can accommodate 27. It means we have to restrict something in our design. This is a very nice thing which we may not find in our mainline working. So we find there are many zones which we cannot discuss here. By zones we mean to say these are guideway elements. So the entire railway system is considered a guideway. So like axle counter, a switch. Switch means points are called here in this country switch. So a point has a point zone. Any area we describe some areas as a conflict avoidance zone. We do not want any operational deadlock. So some area I will define. If this train has initiated, train 1 has initiated its route first, he will occupy or reserve. Reserve is the terminology which is used. He will reserve a conflict avoidance zone. And this conflict avoidance zone will be considered as an obstruction by another train. Like for the main line, what is our obstruction? Our obstruction is any red signal. here the obstructions are multiple things. It can be a train, it can be a preceding train, the train standing forward. It can be any reserved switch zone by another train from another direction, or it can be a reserved means occupied, which we call in mainline, right, route locking down, similar to that. So any reserved conflict avoidance zone, it can be anything. Even a disturbed point can be obstructions. So train moves. So like I gave an example, like if we have to accommodate 32 trains and we have done designs 100% thoroughly with full of our dedications, but we found we can only accommodate 27. Then we try to redesign in such a way whether the switch zone I made this much. Can I shrink the switch zone? There are various things. There are some unavoidable areas, like like we have a neutral zone for the AC electrified, where most of the CBTC systems they run on the 750 or 690, whatever it is, 750 or 690 or 800 volt DC. Now there are some areas where there will be no power supply for say 100 meters or 75 meters, etc. So we do not want a train should stand in this area. So I should declare this area as a unallowed zone. So like suppose there is a crossover, double-ended crossover. I do not want the movement authority should be such that a train should stand in a crossover, because it is not a good area to stand for a train to stand. So when we define those type of areas, we define as a unallowed zone. So what does it mean? When I define this area as unallowed zone, this area or for the 70 meters or 100 meters where there is no power supply, because the track feed which is coming from feed power supply feed which is coming from one area and another area, they are different. So if we declare any area as a unallowed zone, what will happen? System will not give him any target point in this area. That is the meaning. Now I found that in many places I can only accommodate 29 trains, but the clients, the TfL or Transport for London's, their target is 32, and there is the contract. For these only they will pay the money. Then we play those things. Can we shrink the unallowed zone, or if there are multiple unallowed zones subsequently on the path, can we combine them a single unallowed zone? So there are various ways. So this is a very important design aspects which we have to do, so that as Arun sir has explained, a target, but sorry, our headway, basically ultimately it is all headways, but there are various design aspects. Then once we click it, then we may find, yes, we have achieved 32, but some of the requirements we have missed. Then again we have to do this. So this is really a tough portions here. And this I work only in the, I do not know other systems. I know Thelas CBTC system only. For the last 4.5 years, I am working as principal engineer, and from there I can say the Celtrac CBTC system, I think it is almost same system in Hyderabad Metro. That is why I heard, but I'm not 100% sure whether Hyderabad Metro uses the loop. Like here in this project, we are using the transponder, small tag, where the position, all the position geographical details are given. So like here the trains can move in ATO mode, which Ratan Mukhopadhyay sir has explained, means it is driverless, or it can be PM, protected mode. The train will be fully supervised by the ATP, but driver will stop the train on the platform and he can open the doors and he can close. And another is restricted mode, as you understand, in case of a failure. So in case of failure means if the train is not communicating, because CBTC system, if the train is not communicating because of whatever the mistake is, whether VOVC on vital onboard system or communication system or anything, then the train goes in a restricted mode with axial counter being the, what do you call it, backup. Then the axial counter does the detection of the trains. Now in this system, there is one thing which is very different, which I thought I should explain. After that, I will stop. These systems are all requirement-based systems, which when I worked for say 15 years in Eastern Railway, India, I could not see, because we have signaling principles, interlocking principles, and we thoroughly follow them. There is no question. But here, there may be the project where I work. It will be funny if I say there are 3,000, 4,000, 5,000 requirements. Anybody who has mastered in Indian Railways or anywhere in the main line, they will be surprised, because even if we have 100 requirements in a main line, this is too much for us. 100 requirements is too much. Here we have 4,000, 5,000 requirements, and there is a checklist. Once I finish it, then I have to say, is it fail or pass? And there are some requirements and I cannot pass them. Then there is a thing called caveat. We can caveat it. Caveat means one type of taking the risk, but we have parked the risk, but we have to come back to it. So this is a massive thing. So this checklist, there is a checklist where requirement based checklist, and this is the area where we play the role. Then we have to pass, and where we cannot pass, then we have to see, is it a failure requirement or it is a caveat. So once we caveat it, then there are occasions when we find that requirement itself is wrong. There are occasions I challenged many requirements. I said this requirement itself is wrong, and they have accepted. They found, and many requirements here. You will be great to know they have updated, because I challenge them or my other colleagues challenge them. So this is a very new thing. Those who work in the CBTC or this type of, maybe ERTMS also. I have worked ERTMS, different types of systems in Australia, but it is different from European. But this CBTC system has this thing. Another requirement, another thing is, now this requirement, what I said is the guideway requirement. So guideway means the entire train line, entire train system, we call it as if it is a guideway, and we have 30, 40, 50 guideway elements, starting from a point, axial counter, anything is a guide element. And each element we have to define logically its position. I cannot say say axial counter or anything, a switch or a switch zone is here. I have to give it this precise logical definition. What is the logical track? What is the logical loop number? What is the logical position? Each position is 6.25. Then I make a sub position of say 4.8 centimeter. So all these details we give. Then each and every elements are defined. Now this guideway elements has a guideway checklist requirement, and we have to pass or fail. But apart from that, another thing which is done here in this project, this is the Python. Python, I think everybody knows. Python is a computer language which is used mainly for modular type of system, and also will be very, very useful for the artificial intelligence in future. So Python has developed a system here, and that also gives a massive checklist, and it says, oh, your data is now ready, but it has failed 200 or 500 requirement has failed. Now we have to go through these, and we may find out of 500, the genuine failure is only 10. 490, because Python, although it is a good software, but it is a machine language, and it says if he just goes through the requirement, if he finds requirement is even a little bit away, he says it has failed. But there are many occasions where, because of geographical constraint, we cannot put a component in the right place. Suppose where the train stops, here they call it a stopping location. There is no signal, so this stopping location is where the target point, where the virtual or the logical target point will be given. Now from a stopping point where a target point of the train will come, my axial counter should be in a good position, say 6 meter or 12 meter away. But because train front has an image, when a train come, for safety reasons, if this is the train, I will tell the system, no, the train is not here. Train has some extra thing that is called image. So when the train stops, then the image shrinks and only the physical train. So the logical train is bigger than the physical train. So when a train comes and stops in the the stopping locations where his target point is, he still has an image. That image, if my axial counter is very near, that image may protrude to the adjacent axial counter block and may cause an axial counter block failure or etc. So it means I'm just giving one example, and with this I will stop. The axial counter I am supposed to put say at 12 meter away, but because of geographical constraint, I have to put at 10 meter. So Python will say it has failed, but then again I have to go through and then I have to repass it. So what I mean to say, there is a guideway checklist which has some 3,000, 4,000, 5,000 requirements. We have to then there is another machine Python language, Python based requirement, that also we have to go through. Then we have to say where he said it has failed, we have to then redefine, no, it has passed because of this reason. But there are occasions Python also finds, this is my observation even after working so many years, Python also finds some of the requirements which I could not pick up, but it has found. So then, of course, then we have to accept it. Then we have to again, update the data. There are many other things, but I will stop here, I think, because it is almost, yeah. Thank you, sir.
Thank you.
Very good,
Thank
Pinak.
you, Pinak. This effort today was to give a quick run through the CBTC system. It is neither sufficient nor enough. We will have to redo it in more details of the subsystems. But before we finish the session today, first, are there any questions that we have from the guests? Okay, so if there are no questions, I will ask, because we do have obviously very senior people on the guests today, and if some of them would like to share a few quick words, and in future we will obviously have to organize similar meetings to hear more from them. So do you think anyone would you like to say something today? Based on your background, experience, and what you have seen and what you have heard.
Somnath, can I say something?
Yes, please.
Okay. I just like to put my thought. It was a very good effort to have this kind of panel discussion, and we expect that, as you said, that more in the pipeline. So, incidentally, just a few things with my last 3-4 years of involvement with the CBTC system. It is basically the interface requirements which really create a lot of issues, especially with respect to the rolling stock. And specifically, what we are facing, although we have the same contractor, Alstom, for signaling system as well as for the rolling stock, but still there are a lot of issues which are coming in between between the two contractors. And integration related, and then specifically one more thing, what we find that sometimes the client requirements are put in such a way that it is sometimes impossible to meet with. That is, I think, while framing the requirement, we have to be very careful to what we are asking for. There is one fundamental aspect which we face in the railways also sometimes in our, like I remember that Western Railway TMS project, we asked for so many things, it was just not feasible. So we somehow managed to close the contract without paying for many items to the contractor. So that is one point which I think all the CBTC, in fact, it applies to all the projects, not only CBTC, but all the projects which applies the same way. And incidentally, requirements management system is very important. So we are also planning to use IBM DOORS for the requirements management. We are already using it. And secondly, one thing which can really play a good role with respect to interfacing, with respect to the civil contracts and electrical mechanical contracts, is the three-dimensional building information modeling. That is, I think, become a norm in the metro project. And like first you build up a whole line you built up digitally, like a digital twin, and then resolve all the clashes so that when you actually work in the field, you don't encounter any clashes. So this is the few things I think which just I wanted to put my thoughts across. And one more point, like incidentally for all CBTC projects, most of the CBTC projects are using radio frequency communication in the ISM band. Like in India, we are using 5100 to 5500 megahertz band, which has been recently used. That we are using for CBTC as well as for video transmission system from onboard to the OCC for live streaming. Because for UTO mode, that live streaming of videos on board is becoming a mandatory requirement now. So whether we can go for LTE, public LTE or not, that has to be seen. And there was one point which was raised about the point communication from train to train. I think for goods train, this is already tried out in Australia. So I think you can organize some talk on that, about that autonomous train system. So it would be nice if we could get some info on that.
I am not aware of that train-to-train communication in that sense, because in Australia, Oxide may be also able to contribute, but the whatever systems that I have seen, they basically are conventional in the implementation of the modern signaling system. We have ETCS, which is a very conventional system in the sense that it is established, but then, sorry?
I had read one article in IRC magazine or some magazine that that Rio Tinto has conducted some trial with the autonomous goods train.
No. That is what Rio Tinto has done is actually a driverless working. It's not train to train. It is a pure driver, which is basically a ETCS. You can say that it is a driverless ETCS based standards based system. It is very closely ETCS standard based. But it is the main development there is a driverless working in Rio Tinto. Okay, so because normally, sorry.
So we are designing our metro system for UTU.
Yeah, this is not a metro. This Rio Tinto is actually a mining line. It's a huge area, and it is a freight railway system. So it is, but there are driverless systems in Australia. Definitely, I think Sydney Metro is a driverless system.
Yes, and Sydney Metro trains have been supplied from India.
Yeah.
It's from India which has supplied the trains to Sydney.
Yes. There are a lot of locomotives which come, but the systems, you see, the signaling engineers in the systems development is quite strong. I mean, it is unlike in India. We do have a lot of control over there. Control meaning that a cooperation, and it's not as difficult, I believe, here. So at the moment we are having a lot of these new locos being fitted, and also like in Rio Tinto, obviously this is already a very much running system. So there will be some conflict, but it is not like it cannot be resolved. But there is another thing I believe is basically the lack of a standard which is acknowledged for all the locos is a problem. So that part, obviously, if you have some standards brought in place, at least within a country, it may help.
Yes.
But we may have to discuss these issues. Obviously, we will do some. We'll take some opinions on what subjects we should concentrate on quite a lot. And one obvious area that we have not even talked of at all is the area of the telecommunications. Because without the telecom, the CBTC system is just not there. We have not even touched. We have not touched at all on that aspect, which we may need to do. Yeah.
Can I say something? Somnath?
Yes.
I think first of all, I would like to thank all the participants and the esteemed speakers who have contributed, especially Mr. Tuteja, who has been giving very useful comments. I would like to be given suggestions. Suggestions are welcome.
Yes.
Because a lot of questions are coming to me. In fact, in India, Mr. Shankar has a question, Mr. Balram has a question. I do not know why they have not been able to join. So those questions are emerging. And those questions, I would like to list out a few of them. So one of them is the issue of interoperability between CBTC and ETCS, which I think Ratan also touched about. This kind of a strategy is being adopted for NCRTC or Delhi Meerut, this mass transit system, where Delhi to Meerut would be the normal ETCS level 2 or hybrid level 2. And in the Meerut area, it will be CBTC. So how those two systems will interoperate and integrate, that is an area which I think in UK they have done for the channel signaling. I think ETCS both are existing.
They're done in Crossrail.
Yeah, Crossrail, right? So that
Crossrail, yeah.
That particular issue could be useful for people to adopt here. And third thing was about that, which I think Tuteja raised that issue about why not we go in for LTE or FRMCS, because the requirements onboard, especially from the angle of onboard services, those are day by day increasing. And last but not the least is about let us focus on because as Ratan mentioned that the systems are proprietary in nature. So let us discuss the next session. Let us talk only about Thales. So that will make a structured kind of an approach, and we request questions specifically on Thales and the way I think Pinag Das was mentioning about certain issues which he's facing. Those issues could, in Hyderabad Metro, what is the experience there? That those could be shared at least in this forum. These are some of my comments which I felt I think are necessary. And last is about the last but not the least is the most important aspect, the interface and integration. This is the key to everything. And this is key. And this is if you are able to control the interface. In fact, everything in life is an interface. Everything, whether it is our interpersonal relation is an interface. Everything is an interface. So that if you handle the interface properly, things work properly. Thank you, all of you. Thank you so much.
Thanks, everybody.
Yeah. Thank you all for attending this session, and I would think it is quite a good success for me, because this was the first time I thought this may not have the level of attendance, and I would say the quality of attendance has been extremely good to this. So really feel good. There's a good feeling about this whole meeting today. So can I close the meeting unless we have any other points to discuss before we sign off?
Just
And in
one
future,
more
we'll
point
obviously
just I
have
wanted
longer
to say.
meetings.
Just one more
Sure.
point. See, today the reliability of CBTC systems is quite high, and also we are having duplication in the onboard systems as well as the wayside systems. So tomorrow we may see a trend that not to have any backup axle counters. We are by putting axle counters, line side signals, we are increasing the field gear. I think the system may evolve without any backup system. And it will cut down the cost considerably for CBTC systems.
Yeah. Do we really need a physical trend detection system? I don't know. Pinag may be able to tell in absence of a physical sectioning equipment.
All metro systems that are coming in India are coming with a backup axle counters.
Yeah.
It
That
may
have
be
axle
because under
counter,
failure
yeah.
condition it may be needed. That's all, right? Or
That is for the degraded mode of operation. For the degraded mode of
Yes.
operation, when nothing is working and we do not know the status of the point detections ahead, we do not know anything. We do not know how far is the ahead point. Sorry, how far is the ahead train. We do not know, whether any.
If nothing is working, then axle counters will also fail, because if the communication OFC is not working, then everything will fail, because point status communication is through the OFC backbone.
Yeah,
not
yeah,
through
very
radio.
good. Yeah. And so in this connection, I would like to say there are two types of there are two types of communication failures happens. There are occasions when the communication failure has happened, but the CBTC system knows the full status and he can track the trains by axle counter. That is working. There are NCT, non-communicating train, but they are tracked, and there is a total communication failure, and even the tracking is not possible. Even when the axle counter tracking is also not possible, then of course it has completely shut down. But when the CBTC system has failed because of any reason, whether it is a onboard system has failed or something else, but the CBTC system knows the full data. He has the full data of axle counter block, whether the ahead axle counter blocks are occupied or non-occupied. Then he can pass this information. In this case, what happened? He then leads some wayside signals or wayside some indicators to tell the driver to move with, say, 15 kmph speed or something like that.
Anyway, with the experience, I think probably we may evolve into a no ground-based system at all, except for the point machines. This is a very debatable point, so we can discuss in the next discussion.
Yeah. This is a system
Yes,
requirement.
Yeah, and thanks for the panelists making their time and for preparing for these sessions. Thank you very much.
Thank you so much.
I'm signing it off, right?
Pinag, thank you.
Thank you.
Okay, thanks.
Bye bye.
Yes, sir.
Thank you.
Bye, everybody.
Thanks
Bye.
today.